Alright, let's do some example problems just to make sure that we understand how to convert some structures over to the Hayworth projections. And here are two examples, A and B. And the first one wants you to draw the Hayworth projection that would form if 5-hydroxypentanal was used. And then for B, draw the Hayworth projection for beta-D-galactopyranose. Alright, so we're going to have to understand what these names mean before we can actually draw the Hayworth projection. So that means my advice to you is to take these names, draw the structure first, and then figure out how they actually form together to make a ring. If you can't get the actual skeletal straight chain structure down, how are you going to get a ring structure? You can't. So you've got to start with the basics, and that is the basics for these problems. Alright, so let's look at 5-hydroxypentanal first. Notice this is a review of carbonyl lecture. The Al is an aldehyde, so that is a C double bond OH. If you didn't know that, that's problem number 1. I feel sorry for you with this lecture if you don't know that the Al ending means aldehyde. The next part is pent, which means 5 carbons in total. If you did not know that pent is 5 carbons, then you shouldn't have even made it to this class, because that was one of the very first things that you learned in organic. So 1 carbon, 2 carbon, 3 carbon, 4 carbon, and 5 carbon. The next piece is 5-hydroxy. So hydroxy is an OH group. Again, if you do not know hydroxy is OH, you should not be here. You should not be taking this class. Please, don't waste our time. So the hydroxy is OH, and on carbon number 5, that is where that group is located. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and we see an OH group. Okay, so there's the straight chain, and we know that a intramolecular reaction can happen, and this carbonyl can actually react with the OH group if it's far enough down to give us a 5-membered or 6-membered ring. So the question number 1 is, if this forms a ring, what type of ring will it form? So we look at carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and this would be the 6th atom, right? So that means 6 is a magic number, so we can actually get a ring form that happens here. Okay, so how do we draw that? Well, this is the carbon that has the carbonyl bond. And this is going to hook up with the O from that OH group. Okay, so this is where I always like to start. So this carbon is attached to another carbon, that's here, and that one's attached to a 3rd carbon, so that one's here, and this one's attached to a 4th carbon, that one's here, this one's attached to a 5th carbon, and that's here, and that 5th carbon is the one that has the oxygen that connects in the ring. So there is the ring structure. Now, we're leaving off some things here. 5-hydroxypentanal. This OH group is now basically involved in the ring, so that is where that OH group has went. However, we are leaving off something very important, and that piece is this one here. Carbon number 1 had a C double bond O. So there was a double bond O here. The problem, though, is that this basically has been broken so that it can hook up with the oxygen from that OH group. And now we have this O that, of course, we have always put an H on. So we get this OH group, right? So the problem here would be, okay, here's you a structure, draw it in a cyclic form, and it's up to you on how you want to draw it. bottom line. The reason that we don't really regard alpha and beta in this situation is because alpha and betas are really kind of looking at the OH group, whether it's pointing down or pointing up, but it's in perspective of everything else on the molecule. So compared to group 2, is it pointing down or pointing up? So it's kind of weird not to label this as an alpha and a beta, but you know, it's not really a true sugar, number one. We don't see multiple OH groups on this structure. It's just a carbonyl and it's just an OH group, and they've come together to make this ring, and this OH group could be pointed up or it could be pointed down. It doesn't really matter. And the reason that we're saying it doesn't matter is because there's nothing else around it other than carbons and hydrogens, right? It kind of goes back to that story of cis and trans. If you can't compare things that are on opposite sides or the same side, then you don't need to be using cis and trans. And the same thing's happening here. We can't compare this OH group to anything else on the molecule because simply there's not anything else on the molecule. It's just carbons and hydrogens, and that's all that there is. So this OH group we just pluck on to carbon number 1, and we just know that this OH group could be pointed up or it could be pointed down. Doesn't really matter. We don't have to give it a name because we can't compare it to anything at all. There's no really stereochemistry there in a way. Okay, so let's take a look at beta-D-galactopyranose. Now this is a sugar, right? And this is a true sugar that does have beta because it's in the name. It does have a D form because it's in the name. We know that this thing has come from galacto, which is galactose. So hopefully I know what the structure of galactose is. If I don't, then I've got a bigger problem, because if I can't draw the straight chain, how am I going to draw the cyclic structure? So that's where we need to start. We need to figure out how to draw this D-galactose. So I'm going to look that up in that chart, or hopefully I've got that memorized, and I know that D-galactose is a aldose, at least in the beginning. So galactose has the C double bond OH up at the top, and then down at the bottom of this Fischer projection is a CH2OH group. In between these two carbons, galactose is a 6-carbon chain. So there's 4. 1, 2, 3, and 4. That gives me a total of 6 carbons. If I look at the position of the OH groups, I'm going to see that the top one is to the right, the next one is to the left, the next one is to the left, and the next one is to the right. So this is D-galactose. Now I need to take a look at D-galactose, and I need to convert it to a Haworth projection, because that's basically what this question wants me to do. It wants me to take this Fischer projection and convert it to a Haworth projection. And it's very specific on how they want me to do that, because they tell me you've got to use the D sugar, and you've got to give us the beta form and not the alpha form when you make this ring. Okay, so we know from previous videos that we do get a ring involved with a 6-membered ring. So if this sugar has 6 carbons in total, typically this will make a 6-membered ring for us that we can at least start off with looking like this. So this is our foundation that we're going to be laying our bricks. Now what bricks do we need to put on here? Well, I need to go through and I need to kind of understand that this carbon was my double bond O, but not any longer. This carbon is the one that did the hookup. So in order for it to do that, that bond needs to break. That bond breaks, we're left with an OH group. Now we'll deal with this in a minute, but this is how this ring begins to form. Carbon number 2, I'll mark it red here. This OH group is to the right, so that means here this is going to go down. If I go to carbon number 3, we'll mark that one in green. The OH group is to the left. Well, here's that carbon. It's to the left, so that means that points up. Carbon number 4, the OH points to the left, so therefore here it points up as well, so I'll put the OH group there. Carbon number 5, we'll do that one brown, has the OH on it. That OH is the hookup spot, right? So that's my kind of 6th atom in the line. So this is what made my 6-member pyranose ring. So that is the oxygen from here. So no OH group there. And then finally down here off of that carbon, I see a CH2 and an OH group that points off. So this is kind of almost the answer, because what we're leaving off here is the beta. And I need to go back and I need to remember what beta meant. So we had an alpha anomer and a beta anomer. The beta anomer had the OH pointed up. So really I need to take this OH group on that carbon and I need to point it up in the structure. And there is the Haworth projection of beta D galactopyranose. Now, I want to say something here because you could see it in the assignments. What if they gave me beta L galactopyranose? What if that was the case? Well, I would start off with a different straight chain in the very beginning. So this is D-galactose. If I was required to draw L-galactose, we said that we take the mirror image, right? And we just don't take the mirror image of the last one, but we actually take the mirror image of all of them. So this OH group flips sides. This OH group flips the side. This OH group flips the side, and this OH group flips its side as well. So this is the structure of L-galactose right here. So don't forget that, because that's kind of important. That will give you wrong or right answers, of course, depending on these Haworth projections and what they want. And this is where I would start. Now I know it's a pyranose ring, so again I can kind of start off with this 6-membered ring. I know that they want galactose, but this is L-galactose this time. So that means at this carbon, this second carbon in here, this carbon has the OH left, so that means that points up. And the next one, this OH group goes right, so that means this goes down. Notice they're completely opposite of each other, right? That's what the definition of an enantiomer is. That's what the definition of this isomer is, right? We're taking the flip side of it. So in the next one, we did that one in purple. The OH is right-handed, so that means this goes down as well. And then in the next one, that's the hookup carbon, so that's the oxygen that's involved in this ring. And then finally the last one is a CH2OH group, so there is that structure. Now they want the beta form, and in the alpha and the beta mess, we always said that alpha kind of points down and beta kind of points up. So the same thing kind of happens here. We need the beta form, and that's what we draw. So those are some examples of how to draw these Haworth projections. Very similar to some of the homework and quiz and test questions that you'll see, but there you go. That's the story with the carbohydrates. So we'll keep trucking on. We're almost finished again with the material. I just wanted to pause a little bit, do an example problem, just to make sure that you feel comfortable with what's covered so far. So come back for the next video. We're almost finished, I promise. You can go back and read your book or watch that movie, or maybe go out and party on a Friday or Saturday night a little bit later, but we're almost finished.